Hello, everyone. Welcome to the next lecture in thermodynamics. This happens to be the last lecture for thermodynamics. It's on Gibbs Energy. Delta S can provide criteria for whether a process is spontaneous or not. We've done that in the previous lectures where we calculated delta S of the universe, which was equal to delta S for the system added to delta S for the surroundings. We also called it the delta S total. We know if the delta S total is greater than 0, the process is spontaneous. What does that mean? It means the process continues to happen without any more input of energy, like a ball rolling down a hill. Once you push that ball, give it a start, it continues to roll down the hill. You don't need to add any more energy to it. We also established that if the delta S total is equal to 0, the process is a reversible process. It means that the system is at equilibrium. And the delta S total, if it's less than 0, it means that that process will never be spontaneous. It means there'll have to be a continuous input of energy to keep it going, like pushing a ball up a hill. The ball doesn't push itself up the hill. You have to constantly be giving a push, a nudge to that ball to get it to go up the hill. Now this works, but the drawback is that it requires a calculation for delta S surroundings. Well, we're going to talk today about how we can figure out whether a reaction is spontaneous without using delta S surroundings. We're simply going to be using a quantity that is a defined state function we call Gibbs energy. Some people call it Gibbs free energy, but there's no such thing as free energy, so I'm just going to call it Gibbs energy. All we need to do is find the Gibbs energy of the system in order to establish whether it's spontaneous or not. We're also going to discover that you can actually find the temperature at which any process is spontaneous using Gibbs energy. So we define Gibbs energy as delta H minus T delta S for the system. So the change in free energy is always equal to delta G is delta H minus T delta S, or delta T times S. For the system now. These are all system quantities. If a temperature is constant, an important case in engineering, most engineering processes are occurring at constant temperature and constant pressures, we can establish that delta G for the system is equal to delta H for the system minus T delta S. This will be the equation. It's provided for you on your information sheet. So delta G system, if you may, is a measure of the amount of useful energy that is available in a chemical process or from a chemical process. So delta H of the system is the total energy available, and T delta S will always be wasted heat energy, which occurs almost always. In fact, there's always waste energy that's generated in any process. For instance, in a car, we could talk about the energy derived from burning the gasoline in the combustion chamber. We know that there's wasted energy there. If you put your hand on the hood of a car when it's idling, you can feel it. If you're driving in your car, where the useful energy, the Gibbs energy, is being used to propel the car forward, the waste energy in the wintertime becomes very useful because we can use a fan to push air over that combustion chamber into your car, and you can feel that waste heat energy. It's not available to propel the car forward. It's a consequence of the inefficiency of the system. When we have an isothermal process, Gibbs energy, the energy available to do work, can always be calculated using this equation. And all chemical reactions, almost all of them, are isothermal, meaning they all happen at a constant temperature. If it's an exothermic reaction, then the heat energy is being released into the surroundings to maintain the temperature of the chemical system. So Gibbs free energy is not no pay energy, but it's energy that is available to use to do work. So T delta S is the unavailable energy, if you like, that is wasted in the form of heat, and it's discarded or used for another purpose. So Gibbs free energy at a constant temperature and pressure always equals the total enthalpy minus the unavailable energy, which is T delta S. So delta G equals delta H minus T delta S. So I'm going to show you an example here of a chemical reaction involving hydrogen chloride spontaneously dissolving in water. So let's just switch here to my video that I've got queued up here. So let me move this for a second. So here it is. I'm going to run it and describe what's happening here. First thing we're going to do is show you how you make hydrochloric acid gas. If you take sodium chloride and add sulfuric acid to the mixture, there's a chemical reaction that happens that creates a gas. This gas is going to be generated in the reaction chamber here, this flask, and the gas will increase in pressure as it accumulates. And as a result, it'll flow through the tube and it will be transferred into the container adjacent to this flask. So you can see this Florence flask, the round flask, is stoppered now, and we're going to trap that hydrogen chloride gas in this stopper. What we're investigating here is how useful work can be done from Gibbs Energy. And the useful work that's going to be done will be to push water up into this flask. And you're going to see what happens here. As water, and this is actually cabbage juice, which is a natural indicator. Hydrogen chloride gas is in this flask. Air pressure is slowly pushing the cabbage juice up into this flask. And watch what happens when it first emerges. The hydrogen chloride gas is extremely soluble in the liquid. And as it dissolves, the pressure in the flask, Florence flask, decreases, which means air pressure will push the liquid up into the flask. And that is what we call the ammonia fountain. The color changes because of the acidity of the hydrogen chloride gas. It forms an acid, releasing HCl, of course, produces hydronium ions in solution, and that reacts with the pigment in the cabbage juice, turning it red from blue. All right, so let's go back to our lesson now, our PowerPoint. You can see what that reaction looks like, the useful work. When we actually look at the chemical reaction here, the hydrogen chloride gas was dissolving in the hydrogen chloride aqueous. The Gibbs energy is a negative quantity, which is why it was spontaneous. Once it started, it just happened on its own. It's minus 35.9 kilojoules when you do the calculation. This is the finished product. There is no cabbage juice here. This is another picture just showing it. And we talked about what happened. There's the explanation again. Gibbs energy appears to work. It raises the water. So delta G of our system, of the hydrogen chloride gas dissolving in the water, is equal to delta H system minus T delta S. So to show that delta G system, it predicts the same outcome if you use the delta S calculation. The delta S calculation would reveal that delta S would be positive. So what if I take this equation now and multiply everything by -1? I'm going to show you how the delta S of the universe is related to the delta G of the system. So we're going to multiply each of these by -1. There's the resulting equation. Minus, minus, plus, you can see. Now we're going to divide everything by temperature, by capital T. So divide by delta T, divide by delta T. And of course, when we divide T delta S by delta T, the T is gone. Now, you should be aware that delta H of the system, the heat that was generated either by the system or heat flowed into the system, is equal to the minus Q of the system. But if heat leaves the system and enters the surroundings, the amount of heat that enters the surroundings is equal and opposite to the amount of heat released from the system. So Q surroundings is equal to minus Q system. Therefore, we can look at this equation again for delta H of the system. For minus delta H of the system, we can simply replace it with Q entering or leaving the surroundings. So delta G system divided by temperature equals Q surroundings divided by temperature plus delta H of the system. Now remember, Q surroundings divided by temperature surroundings is equal to the entropy change of the surroundings by definition. So we can now replace Q surroundings delta T with delta S surroundings plus delta H system. Or if we multiply both sides by minus T, we end up with this equation. Delta G system equals minus T, delta S surroundings plus delta T of our system. There's the relationship. So delta G system equals minus T, delta S surroundings plus delta S system. And remember, the delta S of the universe is delta S surroundings plus delta S system, which is delta S total. So delta G system equals minus T, delta S universe. We're simply replacing one equation into the other. Delta S universe, remember, is equal to those two quantities, so delta S universe, or multiplying both sides by a minus quantity, we get minus delta G system equals T delta S of the universe. So what this shows is basically when the delta S of the universe is positive, delta G will always be negative. We know that a system is spontaneous when delta G is positive. We now know that a system is spontaneous if the delta G, the Gibbs energy, is negative. That's how those two quantities are related. So under a more restricted set of conditions, a constant temperature and pressure, simple criteria for spontaneity emerges. Either delta S universe is positive, it's spontaneous, or delta G system negative, it's spontaneous. Now, if the delta G for the system at a constant pressure and temperature is positive, the process is not spontaneous, but the reverse process is. If delta G for the system for the process at a constant pressure and temperature is 0, we can assume that that particular system is at equilibrium. So the price paid for this convenience and simplicity is that it works only for processes at constant temperature and pressure. And remember that it's very common in engineering to be designing systems that work at constant temperature and pressure. We can control those parameters and maintain the reactions in reaction vessels at constant temperature and pressures. Delta minus delta G system divided by temperature is equal to delta S total. And again, when delta S is positive or delta G is negative, the system is spontaneous. So delta S total is always bigger than 0, and delta G is always less than 0 for a spontaneous reaction. And when delta S total is 0 or delta G system is 0, we know it's a reversible reaction. We are at equilibrium at that point. If delta S total is less than 0 and delta G system is greater than 0, we know that the reaction is not spontaneous. That means there will be a constant supply of energy required to maintain that reaction working. To calculate delta G of a system for a pressure of 100 kilopascals, we're going to be able to use this equation, which gives you the delta G of the system value at any temperature. Delta G can be obtained if you have delta H and delta S from tables in textbooks. There's tables in your textbooks. And you can find delta H also using delta H values, HF values. That's heats of formation. And you can use Hess's law, which we've used in the past and you used in high school, where the delta H for a chemical reaction is the sum of the heats of formation of products minus the sum of the heats of formation of reactants. And we can find delta S values from S values in thermodynamic tables using the same principle. The S values, the sum of the S values of the products minus the sum of the S value of reactants equals the change in entropy, or delta S. So we have different options available to us depending on what's given. Now you can also calculate delta G from a similar equation using the Gibbs energy values from a textbook, where the sum of the Gibbs values of products minus the sum of the Gibbs values of reactants also equals delta G. Here again is a graph showing the relationship between delta H and temperature and delta S and temperature. You can see that temperature has very little effect on delta H and delta S. That provides us with a scenario where if we calculate delta H and delta S at a temperature of 298 from tables, we can use those same values at any temperature. However, delta G, that's not the case. Delta G is temperature dependent, and that's when we use delta G is equal to delta H minus T delta S, where we plug in the temperature. But using the values for delta H and delta S at 298 will give us a pretty good approximation for the reaction at any temperature, one that will be useful to us. So delta G of any system at any temperature can be determined using delta H of a system at 298 minus T delta S of the system at 298. We're going to simply plug in the temperature here. So those values, remember, come at 298. So if delta G system can be calculated using delta G formation values, the reaction has to be at 298 K. You cannot use the Gibbs energy table for temperatures other than 298. You have to assume when you use those values in the table, they only work for temperatures at 298. For calculations involving a different temperature, you have to use this equation and plug the temperature into the equation. So as mentioned before, you use the numbers in the balanced chemical equation and multiply them by the G values in the textbook. Products minus reactants, the sum of the products minus the sum of the reactants. Same as you did for Hess's law and for entropy. Again, those little circles mean these are under standard temperatures of 298 K, the tables in our book. Of course, there are tables at other temperatures, but we're not going to go there. So again, to emphasize, the equation cannot be used to find delta G system values unless the temperature is at 298 K. That's because delta G, as you can see, is temperature dependent. Delta H and delta S are not. So let's look at an example. Consider this reaction. We have carbon monoxide gas combining with water, liquid, to make, oh, look at that, ethanol. Very useful process. And oxygen. One way of making ethanol. Obviously, a more efficient way of making ethanol. Industrially, we use yeast to ferment sugar into ethanol. This reaction must be more expensive, or else they'd be using it to make ethanol. Now, is this particular reaction spontaneous at 298? This is one way you can make gasohol. Gasohol, again, being a mixture of gasoline and ethanol. Countries like Brazil certainly make huge quantities of gasohol because they have lots of sunlight in Brazil. Photosynthesis can be utilized to make sugar cane. Sugar cane is one of the fastest growing plants in the world. And the abundant supplies of sugar cane can be used to feed yeast that produce ethanol as a waste. Now, the delta G values are in kilojoules per mole for this reaction. Here are the delta G values for ethanol, for carbon monoxide, for water. Now, the delta G values, much like the delta HF values, are 0 for elements. So from Appendix D in the textbook, we can get these values so we can calculate them again using the sum of the G values of the products minus the sum of the G values of the reactants equals delta G. So if we take the minus 175 kilojoules per mole, multiply it by 1 mole of ethanol, add it to 2 moles of oxygen times 0, which really didn't have to do that, but I'm just showing it to you anyway. And that's the blue is in the sum of the G values of the products minus reactants, 2 moles of carbon monoxide times minus 137 kilojoules per mole of carbon monoxide, added to the 3 moles of water times minus 237 kilojoules per mole of water. Doing that calculation gives you 810 kilojoules total. Now that indicates, since delta G is a positive value, that this is not spontaneous. We said in order for a reaction to be spontaneous, the delta G for a reaction system has to be negative. Now you can only use this method again at 298 K because these values that we got were from a table taken at 298 K. Again, I repeat, then that's because delta G is temperature sensitive. You saw the graph going upward. Delta G increases with temperature. Here's the graph. Let's look at an example 1 here. Let's consider this reaction. Is it spontaneous at 298? Use delta H and delta S to calculate it. Here is the reaction, balanced equation. Here are our values for heats of formation and for entropies. Notice again the entropies. The gases have higher values than the liquids. That's fairly common theme. Again, we're going to take delta H this time. We're going to calculate it from the sum of the enthalpies of formation of products, subtract the sum of the enthalpies of formation of reactants, where we define the enthalpy of formation of elements in their standard elemental states as 0. So delta H, in this case, we didn't show it, but we multiplied 0 by 2 moles here. So it was a 0 here because of the properties of elements. Heats of formation by definition of elements are 0. And when we work this out, we get a value of 790.23 kilojoules per mole of reaction. Looks like it's an endothermic reaction requiring energy from the surroundings to flow into the system to keep this reaction going. And perhaps that's why this reaction is not done commercially to make ethanol. Now, delta S, we can use the values again that are given to us in the tables. Some of the heats of entropies of formation, or not entropies of formation, just entropies of products minus reactants, taking into consideration the number of moles as well. When we do that calculation, we end up with minus 0.0468 kilojoules per mole. Word of caution here, whenever you're doing these questions, please make sure you express your delta H's and your delta S's in the same unit. They could have been in joules or they could have been in kilojoules. Most common mistakes made when delta G's are calculated using delta H and delta S values, and delta G equals delta H minus T delta S, is for students to forget to add units. And they end up with an answer that is ridiculous that I'll talk about a little bit later. So there's delta G equals delta H minus T delta S. We substitute the delta G, the delta H value. The temperature was at 298. The delta S value, and we get 804 kilojoules. We still see, since delta G is positive, that this chemical reaction is not spontaneous at 298 Kelvin. Second example here, we go back to, again, an equation that shows one of the most important chemical processes that's ever been harnessed by man, the making of ammonia from atmospheric nitrogen. The hydrogen comes from natural gas, We break apart natural gas, methane, CH4, releasing the hydrogen, making water in the process. We combine the hydrogen and the nitrogen into ammonia. From a purely thermodynamic point of view, you can see that we are actually becoming less random. We're taking 4 moles of gases and changing them into 2 moles of gases. So clearly, that's not a driving force. Let's look at the reaction in detail. We're going to calculate delta H of the system, delta S of the system, and delta G of the system at 298. Is the reaction spontaneous at this temperature? We could have used the table for delta G values to find delta G of the system at this temperature. Could you? Well, it's at 298, so yes, you could. Now, if I wanted to calculate the same quantities at 698, could we use the delta G values in your textbook? Answer, of course, is no. Because that table is at 298 for delta G of the system. Because delta G is temperature sensitive, we cannot use that table to calculate delta G values at any temperature other than 298. At 698, we're going to have to use delta G equals delta H minus T delta S. We're going to have to figure out delta H and delta S, and then substitute the temperature in to calculate delta G to determine if it's spontaneous. Remember the graph showing that delta H and delta S are relatively temperature independent. That's why we can use that little bit of trickery to solve this question. So at 298 K, we get the values, 2 moles of ammonia times the value for the heat of formation of ammonia. Remember the values for the heats of formation of elements by definition, and the elements in their standard elemental states are 0. So we end up with a value of minus 92.22 kilojoules. We can see that this reaction is exothermic, meaning that the system is releasing heat energy that is flowing into the surroundings. The surroundings are gaining 92.22 kilojoules of energy. The system is losing 92.22 kilojoules of energy. Delta S of the system, we can use tables again to figure out, but this time remember the S values for hydrogen gas and nitrogen gas elements are not 0. One of the big differences between calculating delta S and delta H. So doing the math, we can say 1 mole of nitrogen times the value for the entropy of the nitrogen added to 3 moles of the hydrogen times the value for entropy of the hydrogen. The sum of those two will be the sum of the entropies of the reactants. So it's products minus reactants again, just like you did for your enthalpy changes. When we calculate it, we end up with a value in joules, minus 198.6 joules per Kelvin. Recall, though, that delta H was calculated in kilojoules. So we're going to convert the joules to kilojoules by dividing by 1,000 joules in a kilojoule. Why is that so important? Because this is where if you use 198.6 and 92.22, you will get an answer that is wrong. So finding delta G of the system, we just calculated the delta H of the system. We're going to subtract the temperature times the delta S of the system, and we get a value of minus 33 kilojoules per mole of reaction. It looks like, yes, this reaction, because delta G is negative, the reaction is in fact spontaneous at 298 Kelvin. Now, what about at 698 Kelvin? We can see delta G is temperature sensitive. Delta H and delta S aren't. So we can use delta H of the system at 698 equal to delta H of the system at 298 because delta H's are relatively stable with respect to temperature. Similarly for entropy, we can see, again, relatively stable with respect to temperature. The value at 698 is the same as the value we just calculated at 298. So both of these were just calculated. So delta G of the system at 698 is delta H minus T delta S. This makes it nice and convenient we plug in the temperature value at 698, and we get a value of 46.7 kilojoules. So we can see at 698, this reaction isn't spontaneous. Most chemical reactions usually work better at a higher temperature. Well, not an endothermic process. In this particular case, it doesn't. The higher temperature actually slows down the reaction. In fact, it stops its spontaneity. So it's non-spontaneous at 698. So effects of temperature on the spontaneity of a reaction. This is a really good table that summarizes the two driving forces we've just talked about. One of the driving forces for chemical reactions is enthalpy. If a reaction is exothermic, chances are it's going to be spontaneous. Systems want to lose heat energy to the surroundings. Similarly, the other driving force is entropy. Systems that are becoming more random, less organized, more disorganized, tend to be spontaneous. The table here shows you that the delta G of a reaction can strongly depend on the temperature, even when the values of delta H and delta S don't. This dependence exists because of, if you may, a competition between delta H and T delta S. And we said that delta G, when it's negative, the reaction is spontaneous. So when is delta G negative? Well, delta G must be negative when delta H is negative and delta S is positive, because if delta S is positive, when we multiply a positive by a negative, we get a negative. When we add a negative to a negative, we get a negative. So delta G will always be negative when delta H is negative and delta S is positive. So let's investigate this table further. Okay? Keeping in mind delta G is always equal to delta H minus T delta S for a system at 298 K. If both delta H and delta S have the same sign, there's a competition between the entropy and enthalpy driving forces. Now, before I mention that, let's take a look at when we know reactions are never spontaneous. Again, delta G equals delta H. I'm just going to put this equation back here. We can see when delta H is positive and delta S is negative, a negative times a negative is a positive added to a positive always gives a positive. So we can see delta G will always be positive in those circumstances. So the reaction will never be spontaneous when delta H is positive, endothermic, and delta S is negative, meaning the randomness of the system is decreasing. It's getting more organized. So what if, though, delta H and delta S are opposing one another? One of the driving forces is favorable and the other driving force is not. In case number 2, we have an exothermic process with a randomness change that is becoming more organized. What is going to happen? Delta G could be either negative or positive. And the same holds true if both delta H is positive, which is not favorable, and delta S is positive, which is more randomness in the system. You can have either a spontaneous or a non-spontaneous event. So we're going to consider in those cases those driving forces of enthalpy and entropy to be opposed to one another. Now, when they're equal to each other, delta G is going to equal 0, and the system is at equilibrium. Now, in order for a reaction to be spontaneous, delta G has to be negative. Delta G is equal to delta H minus T delta S. The delta G is always negative when delta H is negative and delta S is positive. We've already talked about that. Delta G can't be negative if delta H is positive and delta S is negative. It's never spontaneous. That's case 4 at the bottom. And I pointed that out with respect to this equation. Again, delta G would always be positive in that case, because if delta S is negative, this is going to be a positive. And if delta H is positive, a positive added to a positive gives a positive. Well, let's look at the opposing forces. What if delta H is negative and delta S is negative, if they have both the same? Well, delta H is negative and delta S is negative. It must mean the temperature has to be small to ensure the sum of the two terms is negative. So if delta H is negative and delta S is negative, a negative times a negative is a positive. We want this T delta S to be small so it does not become greater than delta H. We want the delta H term, which is negative, to dominate. And that's important. And that's a case 2 below. So at low temperatures, this negative term stays small. It doesn't get big enough to overcome the delta H. If delta H and delta S are both positive, the temperature must be large, because if delta H is positive, we want to have a large T delta S term, because when we add this positive, we want a large negative term to make delta G negative. So if delta H and delta S are both positive, the temperature must be large to ensure the sum of the two terms is a negative, case 3 below. So you should be able to figure out this entire table by only knowing this particular equation and just applying basic mathematical properties to this equation in terms of positives and negatives for delta H and delta S. When they're when they're both favorable, we know this reaction will be spontaneous at all temperatures. When they're both unfavorable, enthalpy and entropy, we know they won't be favorable at any temperature. It's when the two opposing forces happen that we know one only happens at low temperatures and the other happens at high temperatures for the reasons just given. If both delta H and delta S have the same sign, there's a competition between those two values. The winner of the competition depends on the temperature. A critical temperature occurs when the two driving forces offset one another. And this occurs when delta G is equal to 0. The system will be at equilibrium. So when the system is at equilibrium, we can make delta G of the system equal to 0. And then we can rearrange this equation to find out the temperature at which this equilibrium happens. We can also establish it as the temperature which is a minimum or maximum at which spontaneity will occur. Very useful. So we are going to rearrange that equation. And again, all I've done is added T delta S to both sides. And then I've divided both sides by delta S to isolate the temperature. So the critical temperature can be found whenever we take delta H at 298 for a system and divide it by delta S at 298 for a system. Because again, delta H and delta S are temperature independent for the most part. Now, since temperature affects delta S, high temperature would make T delta S term more dominant. As the temperature grows, that term becomes more dominant. A low temperature would make the delta H term more dominant. If both delta H and delta S are positive, to be spontaneous, T delta S must dominate. We want a big temperature value. Therefore, to be spontaneous, temperature has to be greater than delta H of the system divided by delta S of the system under standard conditions. Temperature is a minimum here. If both delta H and delta S are negative, we want delta H to dominate. We want a small temperature value. So to be spontaneous, the temperature must be less than delta H of the system divided by delta S of the system. And if that's the case, we know temperature in this case is a maximum. Now let's go back to, let's look at example 3, but we're also going to consider example 2. We know delta G is equal to delta H minus T delta S, and we want to minimize T delta S. T delta S will be less than delta H since both delta H and delta S are negative. If delta H is negative, it means it is a favorable driving force. If delta S is negative, it means it's an unfavorable driving force. So the two opposing forces are, are opposite to each other. Temperature is what is going to determine when the reaction is spontaneous. So the temperature will be less than delta H divided by delta S. And that's going to give us a critical temperature, which will be, in this case, a maximum. So we calculated in example 2 previously. We found the values for delta H and delta S. We are now prepared to find the temperature at which the reaction will be spontaneous. And that temperature, below that temperature, the reaction will be spontaneous. So when we substitute the values in for delta H and delta S, we get a value of 464 Kelvin. Now, this is where students frequently make a mistake. If you were to simply divide 92.22 by 198.6 and not change it, you're going to end up with a tiny little number that is a fraction above absolute zero. And that certainly doesn't make much sense. For this reaction to be spontaneous at a temperature of less than 1 Kelvin makes 0 sense. Whenever you see that type of answer, you should automatically recognize that something is wrong. And in this case, it's because you forgot to change the unit for entropy from joules per Kelvin to kilojoules per Kelvin. Now, you could have done the same thing by changing the kilojoules or the enthalpy value for the system into joules. It doesn't really matter as long as they are both in kilojoules or both in joules. And remember, the entropy is always, the unit is always in energy divided by temperature. It's temperature dependent, which gives you a unit of K or Kelvin when you use the equation of delta H over delta S. If you didn't have a different unit for delta S, if it was just kilojoules, units would cancel. You wouldn't have a unit for temperature. That's why you need to have kilojoule per Kelvin in the entropy quantity. Now, does a critical calculation, critical temperature calculation, agree with what we found in example number 2? Well, let's take a look here. From the previous example at 298 Kelvin, we calculated delta G. It was minus 33 kilojoules per mole, showing it was spontaneous. Because it's a negative quantity, we said when delta G is negative, a reaction is spontaneous, or when the entropy of the universe is positive, it's spontaneous. We also calculated 698, and we calculated the value at 46.7 kilojoules. It is not spontaneous at this temperature. So obviously, the reaction is spontaneous somewhere between 298 Kelvin and 698 Kelvin. We calculated just now that the temperature, the critical temperature, was at 464 Kelvin. Does that make sense? Sure does to me. It's in between the 298 and the 698. And that 464 is the critical temperature, which agrees with our findings. Now, it's important that you apply the principles that we have just gone over in this particular lecture. And you're going to find a problem set 2 in the appendix A of your course pack. You might have already started working on some of the problems there. When you're finished them, you can look in appendix B to get the answers. Please don't look at the answers until you do the problems. Another strategy would be to pause this lecture at various points and work out the quantities on your own to make sure you're on the same page as I am, so that you thoroughly understand the concepts involved in calculating delta G, delta S, and delta H. And for now, I want to say thank you for participating, and we'll see you next time. Take care.